A nozzle is a device that converts pressure into kinetic energy by forcing fluid through a smaller diameter opening. Turbines work this way because the fluid, which is usually gas, with a high kinetic energy impinges on the turbine blades, which causes them to spin and allows the energy to be converted into electrical power. So we're told to consider a nozzle that forces 2 gallons per minute of water, so a liquid, at 50 psia in a tube of 1 inch inside diameter through a 0.1 inch nozzle from which it discharges to the atmosphere. Calculate the discharge velocity. And so here we've got a little simplified diagram. Water coming in, going through a restriction in cross-sectional area and coming out at atmospheric pressure. Note that the pressure is higher. We're converting pressure into kinetic energy. The pressure is higher at position 1 than position 2, but the velocity is going to increase. And Bernoulli's equation tells us exactly how that works. One of the common mistakes that I've seen among students before they really start thinking about process fluidics and how fluids flow is they always think that higher velocity must mean higher pressure. And so, for example, when you take a hose, a garden hose, and you restrict with a nozzle, you restrict the flow, the water comes out faster. And the naive assumption is to think that faster velocity is faster, is higher pressure. That's not true. It is at a lower pressure here than what we have here. If it were higher pressure at position 2, then water would flow backwards. So anyway, we've got our given information. We've got a volumetric flow rate of water at 2 gallons per minute. We're told what the pressures are. We're going to keep everything in absolute pressure. And so P1 is 50 psi, P2 is atmospheric pressure, and again I'm kind of mixing and matching my units here just for convenience because I happen to know these numbers. We're given our diameters, and of course we're going to assume that water is incompressible in a nominal density of 1,000 kilograms per meter cube. So we want to find the exit velocity. We want to find the velocity of water at position 1. Our assumptions: this is steady state flow of water. It's also an incompressible liquid, and so the continuity equation applies. And we'll write that continuity equation a little bit. We're going to use absolute pressures. If we wanted to use gauge, we could, but we're going to use absolute because that's what is given. We're not assuming we're assuming there are no head losses due to friction. So sometimes in process fluidics, for a restriction like this, there would be a frictional loss or head loss, but we're going to assume that's essentially 0. And then there's not going to be any head added or head extracted. And so when we apply our Bernoulli equation, this is what we're talking about. There's no head added, no head loss, no head extracted, and so we're just dealing with these terms. We can also assume that because this is horizontal, there's no change in elevation, so our Z1 is going to equal to our Z2. And so what we're left with is to cross out those terms in the Bernoulli equation and see what we got. So what we have is we have our pressure and velocity head on the left side at position 1 is equal to the pressure plus velocity on the right side. We want to solve for the velocity at position 2. So what we need to do is we need to figure this out. We know the pressures, of course, so those are known. This is our unknown, U2, but U1 currently is unknown, and so we're going to have to figure out how to do that. And so there are several ways that we can do that. We can directly solve for U1 because we are told what the volumetric flow rate is. We're told the volumetric flow rate is 5 gallons per minute, 2 gallons per minute. And so we can go through those calculations and we can solve for the linear velocity. So once we do that, we can rearrange this equation. We now know what U1 is, and so our only unknown is U2. This is a quadratic equation in terms of U2, and so what you could do if you're working this on pen and paper, you would need to rearrange this equation, get it in the quadratic formula, and then apply the quadratic equation, and you can solve for it. But we can do this rather quickly in MathCAD by just using the root function. And so what we can do is, to do that, we first enter a guess for U2, and so I put in 20 feet per second, and then I take this equation here, and the reason why I moved everything over to the left side, all the terms, is because this is how the root function works in MathCAD. And so you take the left side, you set that function equal to 0, and then you ask, so here's that function, and then you ask MathCAD to solve for U2 in that function. And as you can see, we get a value of 22 meters per second, or 72.4 feet per second. We compare that, I kind of skipped over this, we compare that to what the entering velocity is at position 1. You can see that as 0.8 feet per second or 0.25 feet per second. You can see that the velocity increases by almost tenfold. So a very significant increase of velocity. You can see that our diameter is decreasing by about tenfold. Our velocity increases by almost tenfold. So note that we did not do anything about the velocity head correction for whether or not we have laminar or turbulent flow. What we can do is we can run through these calculations just to check what kind of flow we have at position 1. So what I did was I went to the NIST webbook and just looked up a viscosity of water, and then calculate the Reynolds number at position 1, Reynolds number at position 2, and what we can find is that this is about 7,100. The transition from laminar to turbulent flow is around 2,300, 2,000 to 2,300, and so we've got turbulent flow at both of these positions. And so we really don't need to do anything, worry about any kind of conversion of or accounting for transition of laminar flow to turbulent flow, because everything is turbulent. So what this does, this problem illustrates how pressure energy at position 1 is converted to kinetic energy, and that is exactly what our Bernoulli equation predicts.